Hey guys, we're going to be taking a peek at a concept called torque. Now, the notes that I give you guys are available on slide 78 to 104 in the notes section. Okay, we're not going to look at the rest of them. We're just going to keep an eye on just these slides. So this is where this information is coming from. So when we look at torques, the first thing that I think of when I'm thinking of torques is, when I'm trying to get a bolt out. Let's say we got a bolt here, and I've got a wrench. And forgive my drawing, but let's say I've got a wrench here, and we'll call that the bolt. And I want to loosen this bolt up. Okay, and and it's stuck. Now, unfortunately, this thing's stuck. It's been sitting around some, salt water, and it's starting to rust up a little bit. First thing I do is I put my wrench on it, and then I grab the wrench as far out as I can, and I pull up on it to loosen the bolt. So I apply a force to the wrench. Now, like conceptually, what I'm doing is I'm actually like spinning something rotational. So I'm actually putting a rotation to this wrench. I'm trying to put a rotation to it. Now, a lot of times when I'm on a job, I get to the customer's house and I try to unbolt a bolt that's been sitting for a while. This sometimes doesn't work. So I apply my force. I try and I try and I try. And no matter what I do, I can't pop that bolt. So what I've got in my toolbox is an old pipe. And this is like an old mechanic's trick, is that when you can't pop a bolt, there's a couple of things you got to do. Number one is I take a pipe and I stick the pipe on the end of this thing like this. And then I apply a force out further from where I did before. And with this pipe, I'm going to draw a little circle there. With this pipe, I'm able to push the wrench up and get more what we call torque, rotational force on this bolt. And the longer the pipe, the more torque I can produce, and hopefully get the bolt undone. Now, sometimes I've got to put some heat to the bolt, and then that's some more physics for you, but physics that we're not going to talk about now. But the more length I have on that we call lever arm, okay, the more length I've got, the more torque I can produce here at the bolt. So if I do apply my force up, okay, in the upward direction, it is going to produce a circular motion, which I can apply this to this way. So the bolt is going to turn, in this case, counterclockwise, which will loosen it. And I don't know if you remember the old term lefty-loosey, righty-tighty. If I want to tighten up a bolt, I'll just bring my force the other way for that. So there's another thing to consider when looking at torques. There's another variable here because sometimes when I'm pulling on a wrench, if I draw a picture of my fingers on this thing, my hand can't always pull it in the 90-degree or perpendicular direction. So I'm just gonna draw a picture here, another picture of here's our axis we call of rotation Okay, there's our axis of rotation. And let's say we'll call this a door. And conceptually, you can understand that if I apply a force here in this direction, or if I apply a force in this, we'll call this F1. Okay, if I apply a force in this direction, okay, this one isn't going to get you quite as much torque. Okay, this one is, but this one isn't. So in real life, we've got different directions as well, in which we are pulling on our lever arm. So my question for you would be which one, F1 or F2, would produce more, or have the door, we'll call this a door, have a greater angular acceleration? And if you guess, you guess right when this is the one that will produce the most. Now this one is going to produce some, but the x component, that's this part right here of this vector, this force vector, is doing nothing to the angular acceleration. The only part of this that is doing anything is the y part. And back from vectors, we learned that the y part is going to be the sine of the angle times the force. So the part that's acting in this upward direction will be F sine theta. Okay, so if we apply an angle to it, that would be called F sine theta. So we're going to get into a formula that's going to, we're going to come up with a formula for torque. And it's a simple formula. Okay, here it is. Torque equals radius. Okay, now the radius is the length of the lever arm. Okay, so that's the length of the lever arm times the force. Now we could leave it this way, okay, if we wanted to, if it's a 90-degree angle, but we're going to add something to it, and that's sine theta, just in case we get into some angles here. So the torque is the radius, the lever arm, times the force multiplied by the sine of the angle to the horizontal. Okay, so we're going to look at torque's units now. Okay, the radius is measured in meters. Force is measured in newtons. We're going to flip this around. We're going to actually say the units of torque. Get rid of that. Units of torque will be Newton meter. Okay, so that's the unit there that we're looking at. So I'm going to give you an example here. Just it's a conceptual problem, but it makes sense. So let's look at our wrench. So we're going to get this wrench going. Okay. Okay, here's the bolt, okay, which is going to be spinning. We're going to be trying to release that bolt from its position there. And we're going to assume that a force is applied perpendicular. So that means that we'll have point A here, point B here, C here, and D here. Okay, let's compare the torques. So, like, what I'll say is, like, at what position would I want to place my hand in order to produce the most torque on this nut or bolt? So, if we look at D, okay, let's look at D. Now, here's the radius, okay, the lever arm of D. Let's say I were to apply for D, 20 newtons of force. Okay, so force is 20, angle is 90 degrees, and and we'll say the lever distance, the radius, is 0.1 meters. Okay, the torque, okay, is the force times the radius sine 90. Sine 90 is 1, so that's just really irrelevant. So torque is 20 newtons times 0.1 meters. Okay, so we're going to come up with a torque of 2 Newton meters. Okay, so here at point D, the torque would be 2 Newton meters. Okay. Now, the conceptual question would be like, well, at which position can I produce the most torque? Okay, D, C, B, or A. And you're going to look at the furthest distance from the end of that, from this point here, as the position where you're going to produce the most torque. So let's say that each one of these radii where are 0.1. Okay, that means that A, okay, the A is 0.4 meters away. It's the longest point of the wrench here. So conceptually, we understand that at point A, we're going to produce the most torque. For the calculation, we can do 20 newtons. Angle is 90 degrees. The radius is 0.4 now, meters. We know that torque, that looks like a J, torque equals force times radius sine 90. Torque is 20 newtons times 0.4 meters. So the torque is 8 Newton meters. Okay, so we've got more torque at the end of this, which is going to, in essence, produce more angular force on this nut. Okay, so conceptually, we know that at point A, you're getting more. In fact, if you wanted to do the good old-fashioned pipe trick, okay, and you could extend that radius, you'd produce more force, more torque on this bolt. So the longer the lever arm, the more torque that you're going to produce. So let's look at some common applications. So, okay, so the 3 common applications we're going to look at. Number 1 would be balancing masses. Second one will be a lever. And the third will be a screwdriver handle. So our applications will be the balancing masses, the lever, and the screwdriver handle. So let's look at the balancing masses first. Okay. Okay, so let's say we've got this situation here, where we're at our fulcrum point. Now you learned that back in the 7th grade. This is able to tip back and forth. And let's say you've got mass B, and then you've got mass A. Okay, so here's a balance with 2 masses attached to it. Block A has a mass. Okay, so we'll say mass of A is 0.67 kgs. Okay, and then is located a distance, an R, of 0.23 meters away from the pivot arm here. A block B has a mass of, let's say, 1.2 kilograms, and it has a radius of, we don't know, actually. So the radius is question mark. We don't know. So my question is, like, we'll call this 1, we'll call this 2. Where can we put this block, this bigger block, in order to balance this out? Now, if you think about it in terms of, like, position, when you're a kid, I'm going to draw a little side picture here. You remember the seesaw? Well, the only way you could, and the seesaw actually had, like, 3 spots here and then 3 spots here. And if you were the big kid, you'd have to sit closer, and then the little kid would have to sit farther away. That's conceptual. That's rotational dynamics. That's torques all the way. The big kid is not going to produce as much torque if he or she is closer to the center. The little kid is going to produce more as they work their way out. So that's just an aside. That's just a little thought that I had when we're doing this kind of problem. So let's figure it out. Okay, we know that this, we want to say this is to balance it. Okay, this has got to be balanced, so it's actually no motion happening. So what I'm going to say is that since it's balanced, now just conceptually look at it, the sum of torques has to be 0. All right, since the sum of torques has to be 0, that means that the torque on side A has to equal the torque on side B. All right, so let's see. Okay, mass. Now, I can't directly put mass in there, but I can come up with a force. Okay, mass times gravity is the force pulling down. And similarly, mass times gravity is the force pulling up. So mass times gravity times the radius, and we're looking at a 90-degree angle here, so radius sine 90, okay, on the left side, on side A, equals the mass of B, gravity, radius, sine 90. Now, I put the sine 90 because I want to get you into the habit of understanding that, yes, it is pulling down at a 90-degree angle, which is a direct pull down. So this is pulling down, this is pulling down there. They're going to be opposite. Excuse me. Okay, so now you're looking at this and you're saying, well, what's the same on both sides? What can we get rid of here? Well, I can get rid of the sine 90 because that's on both sides. The radiuses are different, so we got to keep those. The masses are different, so we got to keep those. But gravity, well, gravity's the same on both sides, so I can actually get rid of that. So I've simplified this now as the mass of A times the radius of A equals the mass of B times the radius of B. So I've kind of made this a little more simple. So let's solve it. let's solve it and see what we got. So mass of A is 0.67 kilograms. Radius of A, we said, was 0.23 meters. Mass of B, 1.2 kilograms. Radius of B is unknown. On the left side of the equation, I got 0.15. It's a unit called kilogram meter, okay, which is not really a torque yet because we don't have a force there, but that's on that side, is 1.2 kilograms times radius of B. So a little simple algebra will tell you to get R by itself, we divide both sides by 1.2. So let's figure it out. Okay, the radius of B, this one here, has to be 0.1, we'll say 13 meters to balance it out. Now let's look at it in terms of the seesaw problem. So the big boy has to sit closer. I know my diagram doesn't show that, but the big boy has to move closer, 0.13 meters, than the little guy who sits at 0.23 meters. And we can do some experiments to relate this, and there's a little lab we can do to show this concept. So, learned about the balance in this situation. So, with balances, I want to make a remark on Archimedes. And Archimedes said, quote, "Give me a place to stand, and with a lever, I'll move the whole world." So I just want to draw a picture of that. So if you have a little fulcrum point here, okay. Okay, and let's pretend that this is the planet. Okay, and if you apply enough force here, or if you get enough lever arm, indeed, you could actually move the world. Now this is, this is an illustration, and we really don't have a material that could be that strong here to do that. But if you could get a material that's strong enough to do that, and also long enough, you could actually lift up an entire planet. Pretty cool stuff. In fact, I'm going to give you a bonus problem that's related to this. I'm going to give you the mass of some big object like the moon. And I'm going to ask you, with a normal human force, how long the lever arm would have to be to lift that the moon. I know this video is carrying on, but we're going to move on. You don't have to watch the whole thing in one step. And I do give these notes in class, but the second one is our screwdriver. Okay, so I'm going to look down at the screwdriver. Okay, so if I'm going to hold the screwdriver, I'll look down at it. And the handle, okay, sometimes they're made with like little bumps on them so you can grab a hold of them. And so here's a screwdriver and here's a screwdriver. Now we'll call this screwdriver A, and we'll call this screwdriver B. This is looking down at it, kind of like I'm looking down at this pen right now, and you're just looking at like the width of the handle. So, which screwdriver would you be able to get more torque out of? Well, this has some radius, and this has some radius. The force that you apply is going to be here. So I can create more torque on this screwdriver handle because it has more radius. Okay, not necessarily more force, but more radius, and that'll give me a bigger torque at the center of this thing. So let's apply some numbers to this. Okay, the screwdriver, as we know, kind of looks like this, and there's like a little head at that point, and then there's the handle that you hold on to. So you're like wrapping your fingers around right here, and you're twisting this thing. So the only way to look at this is like from the downward position. Okay, looking at it like this. Okay, there's the radius. Okay, and then the force is here. And we're going to assume, again, we have a 90-degree angle. We're not going to get too much into different angles here, guys. So the torque on the screwdriver is the force times the radius sine 90. Okay, so let's just put some numbers here. Let's say the radius of that is 0.02 meters. Let's say the force that we apply is 30 apples, or 30 newtons. So sine 90 is 1. So torque is force times radius. 30 newtons times 0.02 meters. So 3 times 2, 6. The torque produced here is 0.6 Newton meters. Okay? Now, I come into a situation often where I am trying to undo a screw here, and I have to take and I have to attach a pair of vice grips to this, really extending that lever arm so I can spin it out and I can create more torque here and pop that screw out.